Hello, good evening. So I am Parth Doshi. So I'll be conducting the session for you today. So I am just waiting for more people to join. So I think we can get started in a few minutes. So Mr. Kamalakar, I see that you have joined. So were you there in any of the earlier sessions?
I was there in the last session, in the second half. I think it
Okay.
was not. We are now week 6, right? I think I
Yes,
joined
yes.
in week 4. Week
So you
4, I
joined in
believe. I was week 4,
week four. Okay, fine.
week number 4. Yeah,
Okay, okay,
second half of the week 4.
okay, okay. Yeah, welcome, Mr. Kamalakar. So how do you find the online sessions so far?
Without online sessions, you will not be able to solve
Okay,
anything, sir. Your sessions are really helpful.
okay,
Uh,
okay. Yeah,
Without them,
thanks.
it will be very difficult for us to understand. There is a gap, definitely. It's not that I'm telling that professor is not teaching well. No, my level of understanding is poor. With your additional teaching, it really helps me.
Sure,
Though
thanks.
I am not present, though I am not present in the class, I watch them later on the YouTube. All your
Sure.
sessions.
Yeah, sure, sure, definitely. So yeah,
It is really
exactly. So
helping me a lot. It's really helping a lot.
okay, great. Yeah, so actually the intention is that like whoever cannot join in that specific time slot, then they can actually listen to the recording and hopefully that will solve the doubts.
Okay.
Yeah, I see Mr. Ravi Kiran has joined. Hi, welcome.
Hello, sir.
Hello. Yeah. So is this the first time have you have joined or like have you joined in the earlier sessions?
No, sir. This is the first time I'm joining.
You are okay, fine. So can you yeah, basically I'll just give a brief introduction about myself. My name is Parth Joshi. I am currently pursuing my PhD at IIT Bombay. I am a recipient of the Prime Minister's Research Fellowship, and as a part of that, I got this opportunity through NPTEL to conduct these weekly interaction sessions. So, uh, so I've been doing these sessions for the last 5 weeks. So this is the sixth week, and so in every week we basically cover problems related to the content for that week, and so those could be similar to the problems that you would find in the assignments. And the intention is basically that these uh, sessions should help you in solving the assignment problems and in general understand the course content better. So welcome and thanks for joining this session. So can you just briefly tell about yourself since
Okay, sure, sir.
yeah,
My name is Sai Ravi Kiran.
yes,
Currently, I'm working in TCS Bangalore as
okay,
an analyst, CI analyst. I'm working as an analyst. I have around 15 years experience in the CAE domain. I'm trying to understand about this 1D system modeling.
Okay.
I'm trying to move into this area, so I'm just learning that course so that it will be useful for my regular project work.
Okay, great. So when you say 1D system modeling, so are you like talking about any specific domain or in general to applicable to any kind of domain?
Actually, I work in NVH area in
I see.
CAE. So probably we will. I'm looking for 1D system modeling in NVH side. Yeah,
I see.
maybe
Okay.
we will maybe getting some kind of future projects in that area. We are expecting. So to understand the basics of the system modeling, I'm just going through this course.
Okay, great. Great. Welcome, sir. So it's a pleasure to have you as a part of this session. So I
Thank you.
was also working in industry for a few years. So I was working at Eaton in Pune.
Okay.
So after my master's. So there I was again working on 1D system modeling, but in terms of like for automotive systems basically. So my basically job was to create system level models for automotive powertrains. So it can be either conventional electric or hybrid electric vehicles, and then use those models to estimate energy consumption or fuel consumption like that. So, and then we had other multiple teams in Eaton who were doing like 1D system modeling, like the way you said, like for NVH purposes, and like basically driveline dynamics for automotive. We were mainly working, our team was mainly working in the automotive context, but they were dealing with like different domains. So some were involved in thermal analysis, some were in this dynamics and vibrations kind of domain. So yeah,
Thank you for the info and background.
yeah, sure. So I think we can get started now. So before we get started, so I think Mr. Kamlakar, I think you had, I think, introduced about yourself. So you were, I think you were a faculty member in an institute, right?
Right. Yes, sir.
Yeah, okay. Yeah, great. Sure. So, yeah, so I think we can get started. So before we start, is like just wanted to ask whether do you have any specific question related to the content for this week?
Yeah, I have one thing.
Sure. Yeah, you can go ahead.
Okay, actually, I'm looking for the Mason's gain formula, which is used to calculate the transfer function. Uh,
Okay.
I have some, I mean, not a clear understanding I got actually. Can you explain with some problems like how we can use that formula? I mean, basically the application part of that formula to get the transfer function on any complex system. Yeah.
Okay, okay. Yeah, I think the formula was missing in the slides. I think, yeah, fine. So maybe I can actually share that. I actually do not have the slides exactly prepared for that. But what I can do is I'll actually try to prepare some slides on that and upload it along with the the slides that I'll be uploading for this online session for this week. Because I actually do not have the slides exactly directly prepared for this right now. But uh, what I can tell you for now is basically that the technique of the signal flow graphs. So you are talking about signal flow graphs, right?
Yes, yes.
Yes, yes. So okay, fine. So it's basically uh, so you understood the technique of signal flow graphs, right? So it's similar to the technique of block diagrams, but it's like slightly a different kind of representation. So it's like a graph graphical network kind of thing. So where in block diagrams we represent the gain values as the blocks, and here in this we basically represent the signal flowing from different node to node, and the signal that is flowing, so we attach a gain value to the basically the so to every branch, and then that's how we represent the um, signal flow graph. And then so there are some concepts like one main concept is like the how to calculate the gain value. So maybe I'll try to uh, draw and explain you to the best extent possible. So sorry, but I actually do not have the formula directly prepared with me right now. But I'll do that. Uh, like I'll upload these slides after I complete this session. So is that okay, sir?
Yeah, yeah, it is fine. Only one thing is like if you can solve a problem, any problem, maybe using this Mason's formula, that would be helpful. Yeah.
Okay, fine, fine. Okay, fine. So what I have done is right. Actually, I have prepared some set of problems that uh, that I had planned to solve for this session. So shall we cover those first, and then maybe if time permits, so shall we go through the that Mason's gain formula problems?
Okay.
Okay. Yeah. So because the thing is that I do not have those problems ready with me right now. So what I can do is I'll solve those problems and upload its solution. I think that would be better for me right now.
Sir, sorry for interrupting.
Yes.
Uh, by the end of the session, I can share with you some photographs which you can give some idea of that. But in the meanwhile, can you share your PDF for what questions you are going to do it so that I will skip those questions and get you the rest of other questions.
Okay. Okay. Yeah. I'm just sharing. Yeah. Usually, actually, I try to put the the
Okay.
problems related to each and every concept, but unfortunately right now I missed that part on the Mason's gain formula thing.
Okay.
So
Can you go
but
to the next slide, sir? Just keep going down so that understand what you want to share. Okay. 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 I think I understand where you are. Okay, sir.
yeah, I have basically tried to
Okay, sir.
put
Let's
some
start
of
the session.
okay, fine.
Thank you.
So yeah, so you have some problems with
Yes,
you.
sir.
You wanted to
I,
put the
I have them in a PDF. I need to take them out and then while we are going through the session, I will do it parallelly and send them.
okay, fine,
Okay.
sure. Yes. So I have basically prepared some problems which I like basically plan to demonstrate how we solve them. So So in this, the content for this week, we have basically the concepts related to block diagrams, signal flow graphs, then state space formulation, which is basically how we derive the differential equations for, like, if we have a certain differential equation, let us say some nth order differential equation, then how do we represent them in a state space kind of form, where we split that nth order differential equation into a system of n first order differential equations, which we can cast them into a convenient form where it can be easily given for a computer to solve. So generally, when we do kind of some like numerical integration of some differential equation which we want to solve it in a computer, so generally we can preferably we would provide the differential equations in a state space form and give them to the computer. So then we had the concepts related to frequency response, where we basically represent the so we have multiple techniques, like one is Bode plot, so Bode magnitude plot and phase plot, where we represent the frequency response function. So the response of a system to a sinusoidal excitation basically. So that, and for sinusoidal excitation over the entire range of frequencies, so what would be the response of the system to a certain frequency. So we represent it in terms of either Bode plot. So that's one of the techniques that was discussed. So, and the technique of deriving the uh, frequency response function from the uh, transfer function that we derive using a Laplace transform approach. So that was described. So we'll go through some of the problems related to that. So the first problem is related to the block concept of block diagrams. So here we have a block diagram, and so our task is to uh, simplify this block diagram and find the overall transfer function for this function uh, for this. So here, so in this problem, so we have a gain 1 upon s square plus s plus 2. So that is one of the transfer functions, and in the feedback loop we have the gain 1 upon s plus 1. So now how do we solve this problem? So here, so the signal in the feedback branch over here, so we are taking the signal xs and then multiplying it by 1 upon s plus 1, and then adding it here over in the summing junction, and using it basically to uh, so as a feedback signal. So then the signal over here would be basically x of s upon s plus 1. So let us call this signal over here as z of s. So what would be z of s? So it would be y
Summation.
of s. So this is the signal that we would write. So now we, for this uh, transfer function over here in the forward path that we have, so we have basically x of s is z of s into 1 upon s square plus s plus 2 Now, since we have derived the value of z of s over here in the above expression, so we will get so now we have the x of s in which is the output on the left hand side, and we have a term of x of s into on the right hand side as well. So we'll take it to the left hand side and we can write that. Now we can simplify this further.
Sir, can you go back little to that slide which you have written? There, if you see, z of s equal to whatever you have written, y of s minus x of s by s plus 1 is understandable because two branches are coming in and one branch is coming out. But
Yes, yes.
when you write x of s equal to z of s by s square plus s plus 2, uh, x of s is going to the right, but there is one more branch that is coming below, coming down. You will not take that?
No, actually the thing is that the value of x of s itself is just directly getting taken and multiplied by 1 upon s plus 1. So I mean the transfer function 1 upon s square plus s plus 2. So that's basically the thing that so zs um, so that is the input to that transfer function, and the output of that transfer function, so that itself is x of s, right? So
Oh, okay.
and this is just being taken uh, by the in the feedback loop. So essentially it's the transfer function is acting on z of s itself, like, and that itself is giving us the output as x of s. So
So it is not like our electrical circuits where at a junction you take what is coming inside and what is going outside. Only unless you have that X symbol, then you write that.
it's not like it's you have some, like, let us say electric current, like this is like some I1 current I1, and then it's like distributed as some I1 I2 and
Right.
I1. No, it's not like exactly like that.
Okay.
So yeah, so I understand what your concern is, but it's not exactly like like the electric current kind of thing.
Okay.
Yeah. So now we can simplify this again further. So what uh, we will get is, so please correct me if I actually am making any mistake. So I am also solving along with you. Uh, so we can expand these brackets, and then so we will get basically s cube plus 2s square plus 3s plus 4 and s plus 1 into s square plus s plus 2 equal to. So the overall transfer function, which is xs upon y of s, will be so s plus 1 upon s cube plus 2s square plus 3s plus. So this should be, I think, 3. So this will be the overall transfer function now. So this is how we can solve the problems of block diagram reduction. Yeah, sorry, actually, sorry for that. I actually did not put up a problem on the signal flow graph. But I'll actually, what I'll do is that after this session, I'll just you know solve a problem and record that and put it up in addition to whatever that we are doing right now in today's session. So now we have another problem related to the block diagram concept. So here now we have to find the overall transfer function. So we can reduce this block diagram into simpler blocks by clubbing together and finding the equivalent uh, block for whatever loops are this thing that we can see. So for example, we have in this block diagram, so we have this part where, so how will we represent the overall block for this combination?
Since they are in parallel, I think we should take G1 plus G2.
Yeah, so we can take G1 plus G2. Yes, because the
And then
signal R of S is being multiplied by G1 and separately multiplied by G2 and then being added up. So the overall equivalent would be basically G1 plus G2 itself. Now similarly, we have this thing which is below, but now instead of a positive sign, we have a positive and negative sign. So then how can we write the equivalent for this?
Subtract them. G3 minus G4.
Yes. So it will be G3 minus G4 itself. Yes. So now we can write so now how we can write it now is that this signal, let us say we call here as Z of S. So Z of S will be R of S minus G3 minus G4 into C of S and C of S is Z of S into G1 plus G2. So we can substitute for Z of S like this way, and then again we can rearrange the terms and club the terms related to C of S, and then we will get basically C of S into 1 plus G3 minus G4 into G1 plus G2. So now the overall transfer function will be C of S upon R of S, which is equal to so this is how we can get the equivalent transfer function for this block diagram. So is this okay?
Yeah.
So shall we proceed?
Yes.
Now we have this question. So this is in context of the signal flow graph. So we need to complete the statements. So first statement is, So signal flow graph is applicable on what kind of systems basically? So we can use signal flow graph techniques only for certain kinds of systems. So which kind of systems are those? Any idea?
Complex systems.
It's actually linear systems.
Oh, okay.
So this technique is applicable only to linear systems. So because the equations that we basically get, those should be algebraic equations. So it's applicable only to linear systems. And then two loops are said to be non-touching only if no common what exists between them.
Node.
Yes, so it's nodes basically. So in a signal flow graph, if we have like let us say like and so then so let us say we have loops like this. So these loops are touching each other because there is a common node here for them. But if there is another loop, let us say like this, then these two loops are non-touching because there is no common node between them. Okay, so we'll move to the next problem. So which is related to the concept of state space formulations. So here we have been given a spring mass damper kind of systems. So there are two masses here, and there is a spring placed in between them, and there is a damper. It is attached to the wall. So we need to first find out what is the differential equation for this system, and then we need to extract the state space form of the differential equations. So now how do we go about solving this problem? So any idea?
First, free body diagrams we have to do,
Yes,
and then derive the, I mean, then get the differential equation.
yes,
After that,
exactly.
yeah,
Yes,
after that we have to put it in the state space form.
exactly, sir. Yes. Yeah, so we have to draw the free body diagrams and then basically apply Newton's second law and get the equations of motion, and those will be basically our differential equations, and then extract the state space form from that. So before we do that, so there we can do some assumptions here. So so there is a floor over here, so we'll assume it to be frictionless. Since it's not explicitly mentioned, so we'll assume that it's frictionless. Then let us say we assume the displacement of this mass m1 as x1 and the displacement of this mass as x2, and we'll assume that x1 and x2 are measured with respect to their equilibrium positions. So any idea why we are stating this explicitly? That any idea why we need we can like make this assumption?
To apply the Newton law.
Yes. So we can apply the Newton's law even though this assumption is not made. What will change with this assumption is that it will simplify our equation slightly. Now, like when we say that this is measured with respect to its equilibrium position, so then whatever the change, the displacement from that equilibrium position, so that will basically directly, we can say that this is the deflection, the displacement change in that displacement that causes the change in deflection. Now, if we say that this, we can also write that x1 is something like this is the origin, this point over here is the origin, and then you can say that this is the x1 is this length, then x2 is this length, uh, and then we can also derive the differential equations using these x1 and x2 values. But now what will happen is that, so any idea what will happen if we use like it this way?
No idea.
Okay. Yeah, so generally, so these are actually some small points, but we actually just generally tend to, say, this is x1 and this is x2, and then just like directly use it. But the key thing here is that they should be measured with respect to the equilibrium position. If they are not, then what will happen? So if we say that the x1 and x2 are measured with respect to like this wall, now what will happen is that the length, so this is basically x2 minus x1, so that will be the springs, let us say that will be the length of the spring approximately. So we'll neglect the additional length of those blocks or whatever, so we'll call that is the spring length. Then to get the spring deflection, we actually need to subtract this length x2 minus x1 from its free length. Let us say this is LF, so that is our free length. So when there is no extension of the two ends of the spring, then this thing is basically that's our spring deflection. So we cannot say that x2 minus x1 in this case is the deflection of the spring itself, because that's actually, so because since x1 and x2 are some geometric lengths, so we need to convert it into deflection by subtracting the free length. Now if we sub if we don't if we do this thing like what I mentioned, like with respect to the equilibrium position, now then we are inherently saying that this thing is already taken care of. So why? Because let us say when they are in equilibrium, we mark their positions somewhere here and here, and then so that is when the spring is, let us say, unstretched, and then whatever distance that each of these individual masses move from those respective positions that we marked, so those will be their net displacements from their equilibrium position. So whatever change in x1 and x2, so that will just directly be the deflection of the spring itself. So it's a small but important point. So we just tend to generally just blindly use, like this is some marks, like this is some x1 and some x2, and then just say something like, just derive the Newton's second law. But um, so do you think this is something that helps?
Yeah, understood.
Yeah.
Yeah.
So we generally tend to overlook this, but this helps us in general. Yeah. So basically, then we come to our free body diagram part. So we will. Um, so I'll just erase this. So first, let us draw the free body diagram of this mass M2. So we have been given that there is some force U acting over here, and so there will be a weight and some normal reaction, and there will be a spring force. Let us say it is called as Fs. Then so let us assume that the spring is in tension in whatever configuration that we are assuming. So that's why we are assuming the force of the spring to be tensile. So now the force acting because of the damper, so what will be the direction of the force acting because of the damper?
It will be pulling back
Sorry?
towards the left. It is pulling back.
Yeah, pulling back, exactly. So that too, if x1 dot, or basically the velocity of this block, is towards the right, then the damper force will be like this. So if we assume that this x1 dot is towards the right, then the damper force is opposite to the velocity. Yeah. So yeah, and there will be another normal reaction. Yeah. So this is how we uh, get the free body diagrams now. So now what will be the expressions for the uh, force of because of the damper and the spring? So what will be the expressions for the damper force?
Bx1 dot.
Yes. So it will be bx1 dot, and the spring force will be what?
Kx2 minus x1.
Yes. Now we can easily write k into x2 minus x1 because they are measured with respect to the equilibrium position. Fine. So then we can now write the Newton's second law here for this blocks.
Then will damper also not get the relative displacement x1 dot x2 minus x2 dot minus x1 dot?
So it will, but now what is happening here is like it's one end is fixed to the wall and the other end is moving. So, but the other end is moving at a rate x1 dot. Now, if the damper was such like, if we connect a damper here, let us say here,
No, if the spring has a relative displacement of x2 minus x1, then the damper also not have the same displacement.
no, if there is a damper like this, the way I have drawn right now, like if you,
Okay.
I mean, I mean basically to show this
Oh,
thing
okay.
which, so
Oh, I understand, sir. Okay, that damper will have that kind
So
of
then,
displacement.
then, so then that damper will have that relative velocity.
Relative. Okay.
Yeah, fine. So then we apply Newton's second law to each of the masses. So the acceleration is basically mass into acceleration is sum of the net forces. So net forces on the mass m1 will be basically the spring force minus damper force in positive x direction. So it will be basically, and for mass m2. So I hope you understand this double dot kind of notation. So it's basically double derivative with respect to time, and x1 dot is similar, like, so this is the set of differential equations that we get. So now how do we convert it into an equivalent state space kind of form? So now how do we convert these equations into an equivalent state space kind of form? Now, even before we go into that, so first we need to identify how many states will be. So how many states will there be in this system now?
You
Two.
mean x1 and x2? Do you mean x1, x2 are the states?
So in terms of the state equations, so we will actually get, so these are two second order differential equations, and so we can decompose each second order differential equation into two first order differential equations. So there will be set of four first order differential equations. So basically, so there will be four state variables in this case. So what will be those? So let us say we call the state variables, like we represent it in a matrix form. Let us say z1, z2, z3, and z4. So let us call this is our, for example, our state vector.
Then what is meant by state variable? I could not understand from the lecture.
Okay. So one concept is basically the degree of freedom. So the degrees of freedom here are two only.
Okay.
There are, so that the two displacements of the masses. So those are the two degrees of freedom. But the states concept is that, so since the governing differential equation for each mass is of the second order, so the concept of state space is that we represent nth order differential equations into a set of n first order differential equations. So if the differential equation is of second order, then have two first order differential equations, and we have two second order differential equations. So it will basically, so that's why we have four uh, differential equations. So the state variables will be basically z. So let us call this state variable. So z1 is basically x1, and then let us call z2 as x2 dot, z3, sorry, not x2 dot. So let us call it as x1 dot. Now, so these will be our basically our state variables.
In general, while solving the differential equation, we would specify them as initial conditions. Maybe sometimes we specify them as in terms of displacement, or sometimes only in terms of displacement, or sometimes one displacement and one velocity condition. Is that what you are
Yes.
trying to tell us? That a state variable mean?
So in
Okay.
a way, yes, you are right. So we need to, in order to solve these differential equations. So the differential equation is a initial value problem. So in that sense, so you need to find out. So for a certain given set of initial conditions, what will be the response? So then, so we need to specify a position and velocity, or displacement and velocity. So yes, so in that sense, right. So we
So
need to
if
know
it is a
the,
third order system, then I will specify the initial conditions as displacement, velocity, and acceleration. X dot, x double dot, or a x triple
yeah. So
dot.
if it's a, yes, if it's a third order differential equation, yes, then we need to specify acceleration also. Yes.
Okay. Okay, sir. Thank you.
Yeah. Now, so using this concept, what we get is basically z1 dot is x1 dot, which is same as z2, and z2 dot is basically x1 double dot. So x1 double dot, we can get it from the first differential equation. So it will be basically k by m x2 minus x1 minus b x1 dot. So z2 dot will be basically k by m. So since we have defined x2, z3 as x2, so then, so let us write all the equations now in terms of these z variables, so that, and x1 dot is basically z2, so it will be pz2. So is that okay? Yes.
Yeah.
Yes. Now similarly we can apply the same logic to the second set of equations. So we will get basically z3 dot, which is x2 dot, which is same as z4, and z4 dot, which is x2 double dot, which is minus k by m. So x2 minus x1 is again same as z3 minus z1 plus u by m. So now we have the set of first order differential equations. So what we can do is represent them in a matrix form. So is it clear how we came to up to this point?
There was a sign change between Z2 dot and Z4 dot. That was primarily because of the sign change between x1 double dot and x2 double dot in the top equation.
Here,
Z2 dot you have written k by m, and Z4 dot you are writing minus k by m.
so
That
that
sign
was
change,
because of the forces, like the
right?
Newton's second law, like so the spring force is like will be equal and opposite. So
Okay, sir.
so that's
It should be 2m, right? I think the mass m2 is equal to 2m.
sorry. Yeah, so yeah, I'm right now. I'm just writing it as like some m1 and m2 only. Yeah, exactly. So it whatever maybe it may be like 2m or 3m or whatever like. So I'm basically just trying to say it is either m1 or m2 or whatever it is. Yeah, in this problem it may be, yeah, m1 is m and m2 is 2m. So we can just replace it here by 2m. This will so let us now rearrange these equations in a matrix form, where we basically write, like, if this is our z vector, so we write basically z dot is some function of z. So z1 dot is just equal to z2. So we will basically get the system matrix as a 4 by 4 matrix. So those will be the coefficients for the first row. Then for the second equation, so then we have the coefficient of z1 is minus k by m, the coefficient of z2 is minus b by m, and coefficient of z3 is k by m. So minus k by m, minus b by m, and again plus k by m. So these are the coefficients of z1, z2, z3, z4. Similarly, we come to the third equation. So z3 dot is equal to z4, and we can write now it as 0, 0, 1 because it's only z4, and z4 dot. So in this the coefficient of z1 will be k by 2m, and the coefficient of z3 will be minus k by 2m. And there will be no coefficient of z2 and z4. We also have a matrix in terms of the coefficients for the like input excitation. So for the first three equations, we had no term related to u. So the coefficients for the first three equations would be 0, and the for the fourth equation it would be the coefficient of u would be 1 by 2m. So it will be this. So we can now rewrite and reconvert these z things into x1 x2 related quantities, or we can just keep it in this form. So what we basically know is what we have defined as z1 and z2, and so this is our basically the state equations that we get. So we have these four state variables z1, z2, z3, and z4. So the general equation that we get, which is z dot is equal to az plus, let us say, bu. So A matrix is our basically our system matrix, which is this thing. So whatever that we have got, the 4 by 4 matrix that we have got, and Bu is this basically this thing.
Sir, looking at your matrix, row number 2 and row number 4, they are nothing but your differential equation, right? Whatever
Yes, yes,
differential equation you are arrived at.
yes, yes, yes.
So what does that row number 1 and row number 3 represent? I have to remember.
So 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 that is basically the first equation.
Z1 dot equal to Z2
So
and
Z1
Z3
dot
dot equal to Z4.
Z1
Okay.
dot is basically x1 dot. So z1 is
Okay.
x1, so z1 dot is x1 dot, and we have defined that x1 dot so x1 dot we have defined it as z2. So then
Okay.
we get basically z1 dot is equal to z2. So that's why the coefficient is 1 over here for z2. And similarly for the third equation, so we have z3 dot, which is basically x3, sorry, not x3, x2 dot, which is same as z4. So since
Okay.
we have defined z4 as x2 dot. So that's why we get the coefficient as 1 for Z4. So does that make sense?
Yes, sir. Thank you.
Okay. So now here we have a problem in which we have to find out the transfer function from the uh, state space uh, matrix. So we have been given the matrices A, B, C, and D. Now how do we find the transfer functions from this?
When I refer to the notes, it says matrix C into Si minus A inverse into B plus D.
Yes, yes. Yeah, so there
Okay.
is a long derivation and you get finally to some expression like that. So did you understand how we came to that, or should we go through that derivation?
Okay.
Should we go through that derivation part, or should we just uh,
Maybe if you don't mind, I would say, see, taking a 3 by 3 matrix and solving it in a final examination, it's very difficult. It is a two-dimensional matrix. We can solve it, but three-dimensional matrix, finding inverse and doing all the necessary multiplications, I don't know how to do it. It takes a lot of time. It's not that I don't know. It takes a lot of time. In such
yes, yes.
a scenario, if answer options are there, is there an easy way to figure out that from the answer options?
There may be actually, like, depending on the if like you can actually so in terms of inverse, like, if you can calculate, let's say, some terms of that matrix, and if, like, we find those are somewhat matching, and then, like, uh,
Maybe.
it's
Okay.
difficult to say because it actually depends on the problem that you are solving. But uh, yeah, I understand that it's difficult to solve. Anything greater than 2 by 2 matrix is involves a lot of work.
Right.
So yeah, I agree with that. But basically, the only thing is that we have to understand what is the method, how we get to that. So yeah, we can actually sit and do all the algebra very diligently, with our own,
There is.
we can take our own time and do it all diligently. But the main intention is to basically just understand how we uh, what exactly we are doing. So let us not exactly get into the entire algebra of
Okay.
solving that. So it's like the main motivation is to basically just get around, like, why we are doing whatever we are doing. Okay. So shall we go through that whatever small derivation that we had, so to derive that formula, whatever that you said for transfer function.
Derivation, maybe you can skip, maybe you can solve directly.
Okay, fine. Fine. So in that case, so then let me just pull out the direct result that we had. So the result, it says, so we have a, let us say, output y of s, and then we have a input, let us say, u of s, so that we get that transfer function. as yeah. So this is the formula that I think you were referring to. So let us call this transfer function as g of s. So we have been given the matrix values for these things. So d is already given to be 0. So then we need not bother about this. Then yeah, so the main thing is to find the inverse of this thing. So this, let us first find what is this si minus a. So before we even get into the details of finding the inverse, so we what is the usual method that we can? So there are various methods of finding the inverse, but if we want to go by let us say if we have a matrix A and we want its inverse, so it's basically so this is the formula as such for finding the inverse. So 1 by mod of A. So mod of A is basically the determinant of A, and adjoint of A, which is the transpose of the matrix of cofactors. And cofactors is like let us say if we have a certain element and then we basically allow, in this case since we have a 3 by 3 matrix, so the cofactor, so let us say for the element, let us say for this element the cofactor matrix will be this. So we remove the row and column with respect to that element and then find out that. So first let us find out what is this. So this matrix Si minus A, so we'll compute it separately. So it's basically a 1 cross 3 matrix, and this will be 3 cross 3, and this is basically 3 cross 1. So the essentially we'll just end up with 1 cross 1, so it's a scalar value that we will end up with. So now, yeah, so just let us look at what will be the thing Si minus A. So Si will be basically S, so the identity matrix, so we will replace each value of 1 by S. So it's So this is our matrix Si minus A. Now we can find out the determinant of this. So it will be, so let me just erase this. So this will be the value of the determinant. Now we have to find the matrix of cofactors for this. So so the algebra will, I agree, it will be very, very tedious. So
Maybe you should started with assuming s equal to 2 and solve the problem. That way, if given the answer options, uh, whatever it would have come, you would have got it. Otherwise, doing this problem in this fashion, it takes at least half an hour time.
yes, yes. But now the question here, the question is about transfer function, not like numerical value of some, some matrix multiplication or matrix inverse or something like that. The thing here is basically that we need to find the transfer function, but through this method of using this inverse.
Okay,
So here we actually need to go through that,
I think
symbolic,
we can
symbolic kind
skip
of a
this
thing.
and if you don't mind, go to the next question because it is matrix algebra and it is supposed that we should be aware of that.
Yeah, of course, sure, no problem. Yeah, we can skip it. So basically, these are the steps that we need to go through. We just need to find out the inverse, and then we'll end up. We can just use this formula.
You have given the enough information on this.
Sure. Now, yeah. So now we'll be moving into the concept of frequency response. So here we have a problem where we need to we have been given the transfer function here, and we have been given that it is subjected to a input uh, of sine 2t plus 45 degrees. So any idea how do we solve these kind of problems?
What the professor has done is he has taken S equal to j omega, and where j is the complex number, and for omega he has given taken omega equal to 2, which is has come from that sine 2t plus 45 degrees.
Oh, this problem has already been solved, is it?
No, it is a different with a different transfer function. He was showing something
Okay, fine. Okay, fine.
different transfer function, different uh, sign input.
Okay, fine. Yeah, so the concept of this thing of frequency response is like we can get the frequency response function by putting s is equal to s is equal to j omega. So the um, we basically get the transfer function from Laplace transform. So uh, we basically get that when we substitute s is equal to j omega, so that will be our frequency response function. So then by putting so this will be our frequency response function. So if we multiply by the conjugate of this complex number in the denominator, then what we will get is so this will be our equivalent frequency response function if we use the complex conjugate multiplication. Now, so this particular frequency response function, it has a magnitude and phase. So so this is called like let us say g of j omega whatever. So instead of writing this as frf, so let us if tf is this tf thing is g of s, then this thing is basically g of j omega. So it has a magnitude and a phase. So mod of g of j omega, here it will be 1 upon square root of 1 minus omega square squared plus omega square. So we find the magnitude of this complex number in the denominator. So that will be our um, magnitude, and then then regarding the phase, so how do we find out the phase?
J omega uh, imaginary number tan phi equal to uh, y by x. That is
Yes.
imaginary part by real part.
Yeah, so here the imaginary part is minus j omega minus omega, and the real part is like here let us look at the numerator here. So it will be basically tan phi is equal to minus omega upon 1 minus omega square. So this will be our phase angle. Now we have been given that the input is sine 2t plus 45 degrees. So the input itself has a certain phase angle, and because of this transfer function there will be another additional phase angle. So the equivalent phase angle will be the algebraic sum of those phase angles. So let us first calculate the phase change because of this transfer function. So that will be tan phi is equal to minus omega by 1 minus omega square. So here we have been given sine 2t plus 45 degrees. So then uh, so here we basically know that omega is 2. So therefore tan phi is minus 2 by 1 minus 4. Just a moment. So excuse me, please. I am getting a call. Hello. Yeah, sorry about the disturbance. So we basically here we get tan phi is equal to 2 by 3. So from that we will get phi is just excuse me again, please. Sorry. Hello. हाँ बोल आईआईटी के अंदर है आईआईटी के अंदर जो मानस बिल्डिंग है ना वहाँ पे कौन सा नहीं मिलती आईआईटी के अंदर जो आएगा बीच साइड में है तो वहाँ पे मानस मानस बिल्डिंग जो है वहाँ पर so phi will be around 33.7 degrees. So our overall output, so it's already has a phase angle of 45 degrees. So in addition to that, so there is a phase change of positive phase change of 33.7 degrees. So then we will basically get the output as so total phase angle will be the sum of those two phase angles, and then so it will be some a sine omega t plus some phase angle. So the amplitude will be calculated from this magnitude equation. So we will calculate mod of j omega so it will be 3 square plus 2 square, so it will be basically 9 plus 4, so it will be 13. So 1 by root 13. So it comes out to be around 0.2773. So the amplitude of the output will be 0.2773 because the original amplitude of the input was 1. So the overall output will be 2t plus, so we have the phase angle as 33.7, so plus 45. So this will be our overall output. So is that okay?
Yes, sir.
Yeah.
Yeah, sure. So let us move to our next problem. So here we have been given a certain Bode plot. Then we have to identify the transfer function from this. So the in general, by looking at the Bode plots, we can try to guess what the transfer function will be based on certain features. So like uh, so looking at the phase plot and the magnitude plot together, so we can guess what the transfer function can be. So what kind of features would we generally look for in this?
This was discussed in the class, the same function. This
The
is an
same question
inverse,
was
yeah,
okay.
inverse function. So 1 by s.
Yeah, fine. Yes,
Same.
exactly. So yeah, I actually, yeah, sorry, I think I missed that. Uh, but basically, the concept here, so the reason for bringing up this problem is that, so by extracting certain features from the Bode plot, so we can guess what is the transfer function. So here the slope of the Bode plot, it is minus 20 decibels in 1 decade. So and then here we have the phase plot, so which is minus 90 degrees. So the basically the transfer function would be basically purely imaginary. So since it's minus 90 degree, so it means it's just something minus j. And since the uh, oh, if this thing was like exactly covered, like the entire solution also was covered.
He has shown different graphs and said that this kind of graph it will be 1 by s, and the other way it will be some constant. Two, three graphs he has shown in the class.
Okay, fine, fine. Okay, fine. So I was not aware of that. Anyway, so then if it is already known to you, so then I'll just skip that.
Okay.
So we basically get the transfer function as 1 by j omega, or basically 1 by s. The transfer function is 1 by s for this. So the next problem is again related to frequency response. So we have been given a transfer function. So g of s is 1 upon 5s plus 1. So then g of j omega will be, and the magnitude of this would be
That's that is coming to 0.04.
yeah. So then the magnitude will be basically 20 log to the base 10.04.
Looks like it's minus 27.9.
Yes.
What is that?
So
Okay.
this is the, yeah, so this is straightforward. So how will the Bode plot for this look like?
So
So if we want to look at the magnitude plot, let us say to start with. So what, how do we proceed with like constructing the Bode magnitude plot for such uh, transfer functions? Any idea?
you keep changing omega and whatever value you get, you plot it.
Yes, yes, that is so that we can get, but like graphically, if we want to construct an approximate plot, let us say, if we want to do that,
Yeah.
so then generally, so there is a concept of um, corner frequency. So, so here, when the if the term 5 omega, if it is much lesser than 1, then g of j omega is nearly equal to 1, and 20 log of 1 to the base 10, so that would be nearly 0. So then this, so the Bode plot will, sorry, the magnitude plot will look something like this up to a certain frequency. And when, so when this is much greater than 1, then for that case, just a moment, excuse me. Yeah, sorry. Um, yes, so if the term 5 omega is much lesser than 1, so then the magnitude of g of j omega is nearly equal to 1 upon 5 omega. So So it's basically 20 log of 1 upon 5 omega. So it will be basically a straight line kind of a function. So with a negative slope, because it's 1 upon 5 omega, it's basically minus 20 log to the base 10 of 5 omega. So then it will be basically a straight line with a slope of minus 20 dB per decade, and this frequency at which this thing changes the nature, that is called the corner frequency. So it will change its nature when 5 omega is equal to 1, or when omega is equal to 1 by 5 or 0.2. So the actual Bode plot will look something different. It will probably look something like this.
But we have, sir, but we have calculated a magnitude of minus 27.9. Where is that? Will be indicated on this graph.
Sorry.
We have calculated minus 27.9 decibels, sir.
So that is for a particular value of omega.
Oh,
So
okay,
that
okay.
is for omega equal to 5.
Okay, sir.
So
Okay,
so omega equal to 5 will be somewhere here.
okay,
So it will be minus 27 something, whatever that you were saying.
okay, sir. Thank you.
Yeah. Yeah.
Understood.
So the actual Bode plot will look like the green curve that I have drawn, and so it should, but the whatever the straight line approximations that we do, so those are nearly tangent or asymptotic to that actual curve. So it helps us in getting the idea of how the Bode plot will look like. So for the actual Bode plot, we need to actually, calculate the value of that amplitude for multiple values of omega and then plot it. So yeah, but if you want to get a quick idea of the nature of the Bode plot, so this is how we generally construct it. And then for the phase plot, similarly we can construct the phase plot also with this. So using the same kind of logic. So we know the corner frequency is omega equal to 0.2. So for values of omega which are much lesser than the corner frequency, so g of j omega would be nearly equal to 1. So we had drawn that the amplitude of the Bode plot will be nearly 0. So the phase will be nearly 0, and so for small values of omega, and then for frequency around 1/10 of that corner frequency, so omega is equal to, let us say, 0.02, it will change its nature and start increasing, and when the value of omega increases to, let us say, very high values, then the transfer function will behave something very similar to 1 upon j omega only. So then the phase is just same as minus 90 degrees. So for very high values of omega, the phase angle will tend towards minus 90 degrees. So then So then we'll draw another straight line for this, and this is omega equal to 2, which is 10 times of this corner frequency, and then we join the phase plot, so between these two frequencies. So this will be the approximate straight line kind of nature of that phase plot, but in reality the phase plot we may look something like this, so nearly tangent to this. So here at this corner frequency it will be nearly equal to 45 degrees, so minus 45 degrees. So that is how we can get the amplitude and phase plots.
Sir, we have frequency response curves, where we do it for different damping ratios. But this Bode plot has not talked of the damping ratio. Is it for a damping ratio of 1? These Bode plots are drawn?
So this Bode plot which we discussed, it was for a first order system. So there we don't have damping because
Oh, okay.
so for a second order system, then that damping part will come into picture.
Okay,
So
okay.
so for a second order transfer function, then we will get those different curves. Nature of those curves will like the frequency response curve
So
for
that's the
forced
reason why
vibrations.
we are seeing only one line here.
Sorry.
That is the reason why we are seeing only one line here. Whereas the frequency response curves, where we have for different zeta, we see a bunch of lines.
Yes, yes. Yes, the nature of those curves will change depending on the damping.
Right.
Yeah, so you're right. So any other questions or comments?
I don't know how much time you will be able to spend for that. I have posted 3 questions on the user forum on that Mason curves.
Okay.
Maybe they're available in the sorry, in the user form along with the answer options. These were taken from the earlier run of the same course by the same professor, maybe a couple of years back. That's where I came first, and but I could not do it, so I'm reappearing now.
Okay.
Okay. So
Okay,
uh,
so then I'll check that. So you have
had we
posted
done,
the,
yeah,
yeah.
yeah, in the user forum they will be there. Had
Okay,
we
okay.
done that, what you call Mason's curve, the first 2 questions which you have considered today, uh, I felt like they don't require that much of calculation. We would have come through that Mason curve rule, Mason's rule.
Okay. Mason's rule for signal flow graphs.
Right.
Okay, so the questions are related to signal flow graphs. Okay.
Yeah, right. Right.
Okay. Fine. So then I'll look at those, and I'll try to answer those
Yeah.
questions here. So, so anything else? So that's all that I had from my side for today. Anything else that you wanted to ask or any comments?
No, sir. From my side, nothing. Thanks a
Yeah,
lot.
Sure.
yeah, only about the signal flow graph for the Mason's rule.
Yes.
Any 1 or 2 problems, if you can solve and upload, then it would be useful.
Sure, sure.
Uh,
I'll do that, sir. I'll post.
Joshi, can you stop the recording?
Yeah, sure, sure.
Okay. Okay. We consider the session is ended, so you can stop the recording. As an NPTEL